Ransomware attacks pose a significant threat to organizations, with attackers constantly evolving their tactics to evade detection. Existing solutions, including static and dynamic analysis, rule-based approaches, and machine learning methods, have limitations in detecting these campaigns. To address this, we present a novel approach that analyzes attack timelines within victim networks, combining malicious activity detections from multiple sources into alert graphs. These graphs provide effective and scalable representations of attack paths, enabling the identification of ransomware campaigns. Our method includes a novel parsing and classification technique for alert graphs, which maintains efficacy despite potentially low-dimension node features. This approach allows for the detection of ransomware attacks throughout their campaigns and adapts to different attack patterns. By integrating multiple sources of malicious activity detections, our method provides a comprehensive and adaptable solution for ransomware detection. The proposed approach is designed to overcome the limitations of existing solutions, which often rely on static or dynamic analysis of malware samples or focus on specific attack vectors. Our method, on the other hand, analyzes the attack timeline and behavior within victim networks, providing a more complete picture of the ransomware campaign. This enables the identification of patterns and anomalies that may indicate a ransomware attack, even in the presence of evasion techniques. The paper presents a novel approach to detecting ransomware campaigns by analyzing attack timelines as alert graphs. This methodology focuses on identifying attacker goals based on potential attack patterns, rather than solely relying on static or dynamic analysis of ransomware binaries. The authors simulate ransomware campaigns using an industry-standard attack simulation tool and collect data from various alert sources, including endpoint detection, network detection tools, and a malware severity ranking model. They develop a unified representation for these alerts, featuring timestamp, risk score, severity score, category, source host, and destination host. The construction of alert graphs involves normalizing alert sources using min-max scaling, updating the graph representation with each new alert, and combining graphs based on host connections. This approach enables the analysis of ransomware campaigns across their entire timeline, capturing data across different stages of the attack. The paper highlights the limitations of previous research, which has primarily relied on datasets from the encryption stage of ransomware campaigns. By analyzing alerts in batches and considering their context within a larger campaign, this methodology aims to provide a more comprehensive understanding of ransomware behavior and improved detection capabilities. This section of the research paper delves into the methodology employed in creating a machine learning model that can identify ransomware campaigns within cybersecurity threat intelligence. The authors leverage a graph neural network (GNN) architecture, which is trained on a dataset of alert graphs constructed from real-world ransomware campaigns. These graphs represent the relationships between various alerts generated by security tools during these attacks. The GNN model comprises an initial embedding architecture, subsequent embedding architecture, and a classifier architecture. The initial embedding architecture utilizes graph isomorphism, GIN, layers to update node representations and a transformer encoding layer to create a graph-level representation. For the subsequent embedding architecture, two sets of 2D convolutional layers and max pooling layers are added to the initial embedding architecture. These layers operate on the outputs of the initial embedding architecture and are used for campaign classification and graph contrastive learning, GraphCL. The classifier architecture utilizes the outputs of the GNN layers and feeds them into a new readout function, a summation aggregator, which adds all node representations to form a graph representation. This representation is then inputted into a set of linear layers and rectified linear unit ReLU activations that output a decision on whether the campaign being examined is a ransomware campaign. The authors also describe their sampling algorithm, which results in a total of 20,638 graphs from their campaign simulations. They evaluate their model architecture by constructing a training set using two methods, one consisting only of specific campaigns from their overall set and another consisting of the remaining campaigns. Additionally, they assess the model's performance against the first 20%, 40%, and 60% of graphs included in each campaign in the testing set, which corresponds to the early, middle, and late stages of the ransomware campaigns, respectively. This research paper presents a novel approach to tackling the challenges of complex systems modeling, focusing on the development of a unified framework for integrating multiple modeling paradigms. The proposed framework, dubbed Hybrid Modeling Architecture (HMA), enables the seamless integration of mechanistic, machine learning, and data-driven models, facilitating a more comprehensive understanding of complex systems. At the core of HMA lies a Bayesian nonparametric approach, which leverages Gaussian processes to model complex relationships between system variables. This allows for the incorporation of domain expertise and prior knowledge into the modeling process, enhancing the accuracy and interpretability of results. The authors introduce a novel algorithm, termed Iterative Model Fusion, IMF, which iteratively refines the model architecture by fusing the strengths of individual modeling paradigms. IMF is shown to outperform traditional modeling approaches in terms of predictive accuracy and robustness to uncertainty. The paper also presents a comprehensive evaluation of HMA using a range of synthetic and real-world datasets, demonstrating its applicability to diverse domains, including climate modeling, epidemiology, and financial forecasting. Results highlight the framework's ability to capture complex nonlinear relationships, handle high-dimensional data, and provide insights into system dynamics. Limitations of the approach include the requirement for large datasets and the need for further research into the scalability of IMF. Future work directions include the integration of HMA with other modeling frameworks and the development of novel applications in fields such as healthcare and energy systems. The proposed model architecture consists of a Siamese neural network, specifically designed to tackle the graph contrastive learning task. This unique architecture enables the model to learn robust representations of ransomware campaigns, facilitating effective detection. To prevent overfitting, the classifier is trained in tandem with the Siamese neural network and graph contrastive learning task. The model's performance is evaluated using precision, recall, and AUC score, demonstrating strong results, particularly in identifying unseen ransomware campaigns. Notably, the approach excels in detecting earlier stages of ransomware campaigns, showcasing its potential in early intervention. However, limitations are acknowledged, such as the model's performance faltering when trained exclusively on smaller campaigns. This highlights the need for diverse and comprehensive training datasets. In comparison to baseline modeling approaches, including graph convolutional networks, GCN, and variational graph autoencoder, VGAE, the proposed model outperforms them significantly in testing sets built from unseen campaigns. This underscores the effectiveness of the Siamese neural network and graph contrastive learning task in capturing complex patterns in ransomware campaign data. The detection of ransomware campaigns is a pressing concern, and this research proposes a novel multi-modal approach to address this issue. By combining alerts from diverse detection sources, the authors create a unified, scalable representation of attack campaigns, enabling tool-agnostic implementation and reducing operator fatigue. This approach is evaluated using various testing splits, with the results demonstrating high precision, recall, and AUC scores ranging from 0.84 to 0.94. Figure 3 highlights the performance of the approach in early campaign detection, showcasing its capabilities in detecting the first 20%, 40%, and 60% of campaigns in the testing set. In comparison, base classification methods such as adjusted GCN, VGAE, and GIN exhibit inferior performance, with scores ranging from 0.385 to 0.55. The authors also explore metric learning-based approaches, involving the addition of noise to graph embeddings, such as edge perturbation and node dropping, to enhance model robustness. While some experiments yield strong performance, the majority struggle when faced with previously unseen campaigns. Notably, the proposed approach excels in detecting early stages of ransomware campaigns, outperforming previously investigated detection methods. Moreover, it demonstrates strong performance on previously unseen campaigns, a critical aspect of a detection approach of this nature. The authors acknowledge the limitations of their work, including the need for further improvement in handling unseen campaigns and the requirement for additional evaluation on real-world datasets. Future work directions include exploring alternative graph neural network architectures and incorporating additional features into the alert graph representations. This research proposes a novel modeling approach that leverages alert graphs to identify similarities between cyber threats, even when the model has not been trained on them. By analyzing alert graphs, the approach can uncover additional information about attack campaigns and predict future alerts. The strong results demonstrate the potential of this approach as a foundation for developing multiple tools and models to combat diverse cyber threats. The methodology is based on the concept of alert graphs, which represent the relationships between alerts and their corresponding threat indicators. By analyzing these graphs, the model can identify patterns and similarities between threats, enabling the prediction of future alerts and the identification of potential attack campaigns. The approach's strength lies in its ability to generalize to unseen threats, making it a promising foundation for various applications in cyber threat intelligence. Furthermore, the methodology's applicability extends beyond cybersecurity to broader graph-based problem spaces, where identifying patterns and relationships is crucial. The results of this research have significant implications for the development of more effective cyber threat detection and prediction systems. By leveraging the power of alert graphs, these systems can better anticipate and respond to emerging threats, enhancing overall cyber resilience.